giving that talk. It's because I work in different departments. So these are the departments that I worked at, and it was psychology, the School of Media Innovation, cardiology, and now with the BC Children's Hospital Obstetrics. So in different areas, and these are also the institutes that I got trained at: big data, signal processing, and so on. And I think I have some nice material for you on data visualization I'm going to share with you today. So what is data visualization? It's simplifying. You're having a complex data in hand, and you want to simplify the complex systems, lots of data. You want to put it in a simpler way to amplify cognition. So this is the bottom line. Complex scenarios amplify cognition easily. And let's go back 5,000 years ago. Let's just go back in time. Let's just imagine that all of us now in the desert 5 years ago, looking at the biggest data ever a human being has been introduced to, which is the sky, the constellations, all these data points. This is the beginning. Just imagine that you're in the middle of the desert, you have all this data at the front of you, very complex, and you want to amplify cognition out of this data. What will be the first thing that comes in your head to simplify this data? How are you going to make sense of this data?
Look for shapes and stars.
Shapes and stars. What else?
These biggest ones.
Biggest ones.
Brightest ones.
Brightest ones. What else?
Look for patterns.
Patterns. So likely, you're going to look at distances. See how far these dots from each other. So this is, we talk about 5 years ago. You have nothing in hand, no softwares, no computers. And the first thing you got to think about is how far these points from each other. And then you're going to look for patterns, as you said. So you're going to look for patterns, and you start correlating whatever you see in the star with something you know here on Earth. Just animals, shapes. You want to find any correlations. You find correlation even with traits. You find correlation with personalities. So you have a complex data and you try to understand that all over the years. It's interesting. But how about we see what the Egyptians did 5,000 years ago? They looked at the sky the same as we are looking at right now, and this is what they recorded. This is the first data visualization. 5,000 years ago. Look at that beauty. And now we call it infographics. Now we are calling it infographics. And that is the hot topic. You have something complex, you want to put it in infographics, because that's how people are going to take it. And look what they've done up there. So, I'm not sure if I can. Okay, nice. So here's. Okay. So here's that circle in the middle right there. That's Isis, the Queen of Egypt. And they presented that point, the circle right there, that right there, here, of Isis, because that is the point with the highest intensity. Circle, Isis, the Queen of Egypt, highest intensity. The one at the right side, just near her, is her husband, Osiris. It's a lower intensity point. The ones at the left side, her son, Horus. And it's copy and pasted because these 2 points, for them, they have the same intensity. At the left, far left, is Phoenix. And Phoenix represents a bird that you can see in the morning and the night, and it resembles a fixed point. So this is a fixed point, the Phoenix, and then you have 2 same intensity, highest intensity second, and then they went for something called clustering. We call it now clustering. So they looked at some stars and they put them in categories. So now you're going to split your data into some categories, and they've done some hierarchy. And you can see these rectangles near each other. They split them together to show differences between them and different way of correlating these clusters with what they are looking at. Unbelievable. That is 5,000 years ago. And guess what? They timestamp it. They timestamp it. That bottom figure is the time. That arrow right there says this is the time when we looked at the sky. This is when they looked at the constellation. And moving from winter, which is 8 months, into summer, which is 4 months, at that particular point of time, we looked at the constellation and we reported it. At that time, the crocodiles start populating. That's how far they go in detail, because it varies. If you go upper of Egypt, crocodile populate in the summertime, beginning of summer, but in the south of Egypt doesn't. So they were in even the north part of Egypt when they reported this. So many details in just one figure. Unbelievable. Can anybody beat that? 5,000 years. So what is required? Definitely we want to provide something intuitive, where everyone can understand. But sometimes the tools that you're going to use are not intuitive. You need to get trained to use complicated tools, softwares, in order to provide something very intuitive, right? Good news is, the human brain is so powerful. We all know that. And we are very good with shapes and patterns. No way. We all know that. Excuse me. Connection between the eye and the brain is so fast. And we have that saying, we all know that saying, one look is worth 1,000 words. Did anybody, if you guys, think about that? Why 1,000 words? Why just 1,000 words? Why it's not like million? Why not it's 10 words? Why? Who came up with this? I really tried to figure out and go back and get the origin of this saying, and I found it in 1911. New York, a newspaper published in New York. And that was the beginning. They said, it's a new, one look is worth 1,000 words. And now I'm going to show you and quantify that value for you. Now we're going to quantify that value. There are two studies that I'm going to talk about them to base our conclusion. So the first study is invasive. This is an invasive methodology. They took a guinea pig and implanted a micro array of electrodes in the brain, and they start showing image by image and reporting the speed of neural response for each image. That was done in 2006. Secured for sure. The guy was a postdoc. He secured a position immediately after the study. He reported 10 megabits per second for each image. So the speed of image is 10 megabits per second. Now, what if we speak about words? Image, words. What would be the speed of reading words? I put here 300 as a max, but you guys can, we are about 150, 200 per minute. But let's say 300 words per minute. If we convert that, we assume that the word is perceived by 32 bits in your brain, assumingly, then you end up with 160 bits per second. So the speed of reading words is 160 bits per second. Now let's do the math. Speed of seeing an image, or 10 megabits per second. Speed of reading a word is 160 bits per second. That means one image worth 62,500 words. That's how significant a figure is. Every figure we produce, every data visualized we produce is so important. It's like you saved 62,000 words, pretty much. That's an invasive method. The other study is it's a non-invasive. It's done 3 years ago, MIT, and they were looking, it was very simple. It's like priming. You show an image, no, non-invasive, show an image and ask each participant, did you see an object? Now the trick is you show it over 70 milliseconds. this is so fast. But they reported that everyone, was able to detect and recognize figures in it. And therefore, the speed, according to this study, was 1.5 megabits per second, way less than the invasive method. But if we do the math again, the speed of seeing an image, according to the non-invasive, is about 1.5 megabits per second, and the speed of reading 160. So one image is about 10,000 words, according to the non-invasive study. Then, now we can say in 2017, one look is worth them more than 10,000. That was like 1,000 words. That's not true. That's obsolete now. It's more than 10,000. Now we know how important a figure is. Now I'm showing you scientifically that every figure counts, really counts. If you care about the figure and you produce it in a way, you're saving so much text, right? Now we are convinced, I believe. We are not, so it seems like we are not wired to read fast. We are wired to visualize fast. And there are many awesome tools out there. These tools are helping us to do what? To produce a figure. What type of figure? What that visualization that we want to produce? There are 4, well, I'm saying now it is 4. Maybe later on it's going to be different. But at the moment, to my knowledge, we have 4 types of data visualization. We produce a data visualization to analyze. So you produce a figure, and that figure, the purpose of that figure is to analyze, to make you think. Like what? Like bar chart, heat map, bullet, line graphs, and so on. Give you to look for trends and patterns, for sure. And that helps you for sure to make a decision. This figure was produced to analyze, published last year, 2016, November 9th. Where? The Economist. What is important? What do you think about that figure? What is unique about that figure that makes you analyze? Why? Triggers some analytical...
Show you a change.
Yeah, it shows change over time, right? You see a candidate at 2 a.m. morning on the 9th of November moved into wedding within a window of 2 hours. Another candidate is going down within 2 hours. That's a big deal. It's an investigation based on that figure that I'm just showing you is happening right now. Why that happens? For sure, that's one of the most important figures produced last year. It makes you think. Right now, everyone here is analyzing, and God knows what the analysis is. Everyone. Yeah, what happened? 2 hours. Yes. So this is produced to analyze. Okay. You produce a figure to discover something. And here's the beauty. It's like you're taking 2 different data sets and you start looking at both data sets at the same time. Why? Because you want to discover some correlation. You want to discover some causalities. I'm going to take the same figure again. Here's in the middle. And I'm going to look at the Mexican pesos per dollar. Both data sets, these data sets are completely different. But I'm going to take them and line them by time so I can look at them at the same time and see if there is any correlation, any causalities between what's happening in the States and what's happening in Mexico. And you can see there is some correlation, and perhaps we can say causality here. Okay, we produce a figure to tell a story. Without even saying a sentence, I'm going to convince you in healthcare, especially in healthcare, I will argue that also this perhaps the second famous figure for last year. A figure that shows the correlation between health expenditure, and life expectancy. These are what the governments are doing. All the governments around the world are competing to increase the life expectancy. What is interesting about that figure? Now, look, you guys, I'm showing you a figure, and that figure is to tell a story. So I want you to tell me a story from that figure.
There's diminishing returns on investment.
Yeah, give me.
So basically, the more, even though they're investing more and more, the impact on extended life is
Yes.
reduced.
Yeah. I need another sentence.
There's an increasing gap between USA and these other well-off nations.
Yes. Anybody else? See, a country like Chile spending $1,000 per citizen, achieving 82 years old of age per citizen, where a country like US spending 9 times of Chile per citizen, achieving what? 79 years old. Okay. Now we're gonna speak about, it's a lifestyle of the US. Is it? Believe me, you can write a beautiful essay here. Takes like 3 pages, 4 pages, comparing lifestyle. What's happening? Is it because of politics? Is it because of the lifestyle? Is it because of the food? Is it what is it? You look, where is Canada is right there, spending about $4,000 a year per citizen, achieving higher than the States. That's unbelievable. And so on. And you look at Japan, at the top of that. Why the Japanese are doing this? And governments look at that figure and start analyzing, telling stories about what is happening, and inferring lots of information from just one figure. Interestingly, that figure is famous and it's great because every line you see is normalized by years. So the period of 1970 to 2014. So if I go here, that line here for the US starts in 1970, ends in 2014. For Chile, starts here 1970, ends 2014. Which is an interesting way of presenting 3-dimensional data into 2-dimensional data. So this is a 2D figure, but presenting 3D. And there are many famous scientists who are using this as bubbles, and they make it a movie. And these guys came last year, and they said, you don't need to do all of that. I can just put that in one figure. You don't need to do a movie. You don't need to make a bubble chart, and it's like moving like that. No. Here you go. Just normalize by period. Interesting. Okay. So we produce a figure to teach. And we all know that, and especially in the medical field. A beautiful chart like this, a relationship with left ventricle volume and the intraventricular pressure. Yes, the systolic pressure and the diastolic pressure, that we all memorize this figures. Any medical cardiologist, medical doctor and cardiologist, anyone in healthcare, you have in their head these figures of textbooks in their head and many arrows in there. So if you're providing a figure to teach, well, you need to produce something to show dynamics, movements, and you have to explain it. Put some arrows there, explain exactly what. So that figure is produced to teach. So you have to put so much effort to make it memorable. Change the color. So know what's your target, what's the purpose of your figure? Is to analyze, or to discover, or to tell a story, or to teach. What exactly the purpose of what you're doing? The common ground of whatever you're going to produce is something very important, which is visually quantify differences. You have to produce something you visually quantify differences. And I'm just going to discuss this from my point of view. And I'm going to say we have 7 relative differences, like 7 attributes to show differences. And I will start with number 1, color. We use color to show differences. Yes, but wait a second. How many of you agree, how many of you think that the saturation of figure B is twice or 2 times bigger than the saturation of figure A? 3 times. 4 times. 5 times. You see? 1. 6 times. We use color every day to show differences. We use every time we produce a figure, we use color. And now we're stuck. We don't know what to answer. So color is not a good idea. If you want to show differences, if you have a figure, and you want to, these guys, this is the 20% that's going to make 80% difference in the figure you produce. So please just be careful here with me. 20% I'm going to share with you going to make an 80% difference. So now you see that the color is, you cannot quantify the color. And it's very difficult. How about we go for volume? How many of you think that the figure B, the volume of figure B, is 2 times bigger than volume A? How many of you? 1, 2, 1. 3. 3 times. 1. 4 times. Wow. Okay. I'm gonna tell you that. Area. How many of you think that it is 2 times bigger than A? 3 times? 4 times? 5? 5? We can't. It's almost. Okay. Slope. If you're gonna use slope in your figures, okay, can you tell me if it's the slope of figure B is 2 times bigger than the slope of figure A? 3 times. 4 times. Angle. 2 times. 3 times. 4 times. Length. I'm going to use length as an attribute to provide my data visualization. Okay. 2 times. Oh. 3 times. 2 times and a half. 1. 2 times. 2 times? No? No. It's 2 times. Like, now we partition the length, and you have reference points, so you can see that A and B, and I believe you can figure that it's actually 2 times, right? So if we rate them down, if you want to rank these attributes, you gotta find that the positioning was the highest, and length the second. And then angle, slope, area, volume, color, all these attributes is going to be a little bit inaccurate. And guess what? Why it is inaccurate? Because all these figures, it was 2 times bigger, 2 times bigger, 2 times, 2 times, 2 times, 2 times, 2 times, and the saturation was 2 times.
What do you mean by saturation?
You know the hue and the coloring? It's the same color, but you see difference. It's like you played with colors before? Okay, so it's like filtering, you know? So it was very difficult, for sure, for the color. So you have to be very careful what attributes you're going to use when you produce your data visualization, your figure. And happened, like this is a nice paper published, I believe, 2 years ago from Harvard, and they've done a study over 2,070 data visualizations. And they are also in agreement with us in a way. I need to move. For the news media, you're going to see that the bar chart, which is like the length or position, was the highest, the most used in news media. The second was lines, still lines and closer to bars. And for governance and all the organizations, also the bar chart was most used, and the second was tables. Now, if you go to infographics, interestingly, they use tables according to this 2017 studies. And the scientific publications, they use diagrams. You know, you have a block diagram, say that block, and you have an arrow, block, diagrams like this. So this is the most used. It's interesting to know also what the audience here, if we say news media, that means the majority of people with no knowledge can understand, can visually quantify differences using bar chart, the positioning that we just discussed, and the attributes, the positioning and the. But it depends on also the audience. I believe here we're targeting most people, like we're trying to target everyone to raise awareness or to whatever your target is. One thing also is missed when we produce data visualizations is coloring. And guess what? We have like 8 to 10% of males. They are red-green blind, color blind. They pretty much see these two colors up there, the green and red. You see them exactly at the bottom too. Anyone here see these two colors the same as the bottom two? No? Okay. I'm gonna test you. I'm gonna test you right now. How many of you see 21 on the left figure? How many of you see number 21 on the left figure? You see? Perfect. How many of you see number 35 on the red and on the right side figure? 1, 2, 3, 4. So guys, whoever saw these two numbers, either 21 or 35, you really need to contact or see ophthalmologist. I'm not joking. And just go and do another test. They call it the dichromacy. Okay. So if you see them, please just go and see a doctor. Okay. So this is important, and that's what came. That's what came in Nature. So in Nature 2 years ago, actually 2014, what happened is they said, and this is coming scientifically in Nature, instead of using green red, use green magenta. So when you produce a figure, think about the 10% males who are colorblind. So instead of using green red, use green magenta, please. Okay, how to choose a chart? Well, this is a nice way of looking at charts because I come from computer engineering, computer science background. I like to see charts like this, a flow chart, and say, yes, if you're looking for distribution, you go for histogram. If you're looking for composition, you put just line overlaps, and if you're looking for relationships, you go for scattering, and so on. I will have a presentation, which is part 2 later on, to show you how to choose your charts. But this is just an idea. How to present a chart? Okay. If you're working with lots of data and the goal is to produce one value, just produce one value. You don't need to complicate it. If it is one value, just one value. Here you go. World Health Organization, WHO, they showed one number right there. They said 352 times more health researchers in high-income countries than in low-income countries. That's one value, but that's it. You have lots of data, collected data from all over the place, and the analysis there was just one value, 352. That's a lot. Unbelievable. Let's now assume that we're going to work for WHO. And we are working on cardiovascular diseases, and we found that 31% of deaths caused by heart disease and stroke. Right? This is what we have. We've done lots of analysis. We got lots of data from all the places, all provinces, different states. The result is 31% of deaths caused by cardiovascular diseases and stroke. How are we going to produce this to the public? How are we going to visualize that? And now we're going to compete with other organizations, see how we are, how we did. Anybody?
One in three of you will die.
Huh?
One in three of you will die.
That's right. That's yes. 1 in 3. So he said, here's 30%, and I think that 30% I can present in a different way. How about I say 1 in 3? Because 1 over 3 has about 53%. That makes sense. So yeah, 1 in 3. That's more effective, isn't it? Yeah. Instead of just going with a very low number because it's below 50%, and if I go and say I have 50%, it's like, no, we want to hear big numbers, man. That's sorry.
2 in 3.
Or maybe you look at it from the other side. You want to join 2 and 3, Yeah. So 1 in 3 is that's a good idea. Let's see what other organizations did. Million Hearts. Very famous organization. If you go to the website, this is what they put there. It's a huge organization, too many people working on this project. And they produce it, as you see, 1 in 3 in the United States, they have died because of cardiovascular disease. So the upper part is fine. Can anyone tell me what's wrong with the bottom part?
It's hard to interpret the difference.
Exactly. They didn't know the attributes. Because if they knew what attributes to use, area is not a good idea to show visual differences. It's hard to tell what cardiovascular disease square from the big square. I don't know how to quantify that. I mean, you already told me up there. It's kind of redundant too. So what's wrong with the under 65? Do you guys know what's the percentage of that? Nobody knows. So they were nice with the first part, but they weren't lucky enough for the bottom part. So they needed to take the class. So now, here's another one. Here's Be There San Diego. It seems that these guys are Canadians because they love donuts. So they produce 1 in 3 deaths in a donuts chart. Do you guys like it? How many of you like this? No? Like it? Okay. Is it clear it's like 1 in 3 deaths of what? Don't know. It's a cardiovascular disease or what? It's like, I have no idea. It's nice, but Let's go to watershed health. I'm going to start by asking, what did you like in this video? How can we improve it? If you just gotta say, guys, like, I'm gonna suggest a few things for you to improve. What will be these suggestions? Proportions, like, yeah. Tell me more.
Like they should be the same size.
Yeah, it should be the same size. So putting one for, like, foreground one is maybe not a good idea.
It's not obvious it's a stroke. It could be 1 in 3 people are very happy.
Yes. Yes, absolutely. Yeah, can be interpreted that way. So yeah, it's like even the gray ones are like, who's like, which one is positive, which one is negative? I don't know. It's like these two gray people in the back is just unhealthy, or I don't know. So how about the heart? Usually this heart, when you draw it this way, is correlated with what? Love, right? So that wasn't a good idea. How about you go for heart and vascular? This is Memorial Heart and Vascular Services. Guys, please tell me, how we improve? What's wrong here?
Because word doesn't mean anything. No offense. It's not saying anything.
It's not saying
The biggest text in the image
yeah.
is saying something that doesn't mean anything. So where do the eyes go first?
Yeah, so exactly. So when you have a figure like this, the eyes go immediately to the figures. And they quite like these sticks already, you ignore them pretty much. So I've seen the three persons, and I've seen number one. It's like, I don't want to even read what's written there. So you have to be careful when you produce something like this. So number one, do you think what number one is like more positive, right? Number one, death. and it's right. So sending the message, just we need to be a little bit careful. American Medical Association. Any suggestions?
That's not really clear. It's saying 1 in 3 heart disease deaths.
True. Anything else? Coloring.
Green color encoding talks about organic sustainability. So there's not impact to the message.
Thank you so much. And this is the American Medical Association. Guys, you have no idea. Too many people are working there. Okay, Ohio. How about that? You guys like this figure? Kind of? Not bad, huh? Maybe the heart is okay. Let's go to bar chart. And bar chart is to show differences, right? You want to see some differences. And I'm showing here a paper published in 2015 in a high-impact journal, which is Nature Scientific Reports. And when you show a figure like this, why is not right about showing you have 4 variables? Don't worry about what they present. Just you have 4 variables and nothing, and you have a big one bar there, and then it's like, that's nothing. So what's wrong about that bar chart? Do you really need to present it that way? So I guess that you have the data and you want to produce a data visualization. Do you think that's a good way? It seems like there is one parameter which is the most effective here, right? The significant parameter is the one, and the second one, right? So why are you showing the other ones? It's one value. Just produce it as one value. You don't need to make a bar chart for that. How about here? This is published also in Scientific Reports 2 years ago. Actually, last year.
It's really difficult to compare them because they're all different bars.
Absolutely, I cannot compare them. What else?
It's
Too
too much.
much?
Yeah, it's like,
It's lots of information right there. What else? Too many bars. Can you guys read the labels? The labels are like, oh my god, like how can you produce that? Like even for yourself, when you produce that figure for yourself, I was like, oh my god, I cannot take that figure and go to my colleagues or whatever, or like my supervisors. I know. You see, you have to think about it once and twice before I produce a figure like this. Right? It's complicated. Perhaps the suggestion will be split this into 2 figures and zoom in on the left one so I can see the amplitude and perhaps I can compare in terms of coloring. It wasn't a good idea. And about the coding, like I don't know what green is and what yellow is. I have to go up and look what green is and yellow is. You have to make it easy for me to read and understand. It's 62,000 words. I cannot get them.
How would you put it then? So if you had to put that much data in one figure, how would you do it?
Actually, here is another one published in PLOS. PLOS is a very respected, highly reputable journal as well. What's missing in that figure? The which axis? The y-axis. We don't know what the y-axis is about. I mean, we really appreciate it as simple. I can get the control, simple, comprehensive. I appreciate the amplitude, putting all the values, but I have no idea what the y-axis is about. Right? That was published in 2015. Box plot. Box plot is also about showing differences. And once you provide box plots, you really, really need to show differences and quantify, not just visually, you have to quantify how much of difference. We call that statistically significant. The minute you have a box plot, you go immediately for statistically significant. Here is a chart, box plot, published also about 3 years ago. Do you see any difference? First of all, I don't want to ask for statistical significance. I'm asking, do you see any difference visually between these parameters?
Last one is over.
Man, you have a very good vision. I can't. I'm old now. I can't see this. No, it's very difficult to see. It's very difficult. So before you produce a box plot.
But maybe that's the point, right? To show no differences.
Well, in this case, just report it. If you're taking one figure out of the if you don't have a significant, show whatever is significant, and just say we didn't find significance, right? If everyone sees like I'm going to report the non-significance with a figure and the significance with a figure, that's like the whole. You need 2-3 papers. And usually, if I want to put it to you, if you want to produce figure, it needs to be also positive. Like you always put a figure or image of you or somebody always with positive stuff. Right? You don't show something negative. You just write it. That's like let's say that's a rule of thumb. Okay, here's a figure. Oh, that's also published in scientific report, and there is some differences, and you can see that's like. Shifting and the average, you can see that the average of the sample is moving from here. I can see that, but still, you didn't quantify it. And by quantifying, you say the statistical significance. You say it's a p-value, right? You see the difference between the two samples is p-value off, and it has to be less than 0.05 or 0.01. We're going to have also one lecture on statistics, just introduction. This is going to give you like a very good background on how to do stats easily. But in here, you need to provide p-value. And yes, I can see some differences, but I don't know if it is significant or not. How about here? This is published in PLOS. And it says that the p-value between the green and the orange is less than 0.01, which is high. This is like just high significance. Also shows between the orange and red is 0.001. Between the green and red, less than 0.01. Do you guys visually see that difference? Immediately you say, oh, there's something fishy with that figure. Why? If it is less than 0.001, that means it's completely separable. Right? But now I see overlaps. I see complete overlap here. They failed in producing the figure. Something fishy about it. Here is a figure that shows some differences, and they wrote above the two samples the p-value. You like that, you appreciate that. because I visually can see difference between the two samples for each parameter. I can visually see that, but also I can quantify that by p-value. I really appreciate doing that. Thank you. These guys are the best. This is how to produce a box plot. They looked at normal and tumor. The sample size of the normal was 5 samples. The sample size for tumor is 40. And then there is some difference, and they quantified that difference by saying a p-value of 0.0061. You really appreciate a box plot like that. It gives you the number of samples. Because in the analysis, when you have two samples, I think this is a little bit biased. Why? Because the sample size here is higher. It's far more, like 40 and 5. There is a huge difference. It's called bias, right? So that it will make you think, but you appreciate the honesty. These are very honest people, right? The better situation is like they use more normal to make it more balanced, like 40-40 or maybe less than 40 by 2 or 3. And they reported the p-value. I hope that stuck in your mind as well when you produce a box plot. Pie chart. What's the most famous? This is the most famous, or the second most famous pie chart. Why? Anyone? 2008. Huh?
Is that when the iPhone basically came up with the first iPhone?
Sorry?
That's when they first came up with the first phone.
True, but now it's about the U.S. smartphone market share. The way they produce the green section is Apple, and he put that green section on the foreground to show that it is the second in market share. Right? You don't feel that do you feel that the 21 is more than 19? Do you feel? No. You feel that the 19 is more than 21. That puts it in the second place after 30%.
Others doesn't count.
Sorry?
It's others.
Yeah. And the choice of blue, you see, even the coloring, it's everything, is calculated when you produce. Usually, do not go for 3D pie charts. It's not a good idea. It's deceiving, right? Because the foreground is gonna look bigger. But if I'm gonna produce that, I'm gonna put a pie chart and I'm gonna put it in descending order. Say 39, other is 21, Apple is 20, and I'm moving down in a clockwise descending order. That was a disaster. That came 2012, and you have to tell me what's wrong with that figure. Please tell me. I know it's in Fox. Look, I have nothing against this guy. It's against the pie chart. What is wrong with that pie chart? It doesn't add up. That actually adds up, but more than 100. Like a pie chart should be. The total is 100. How 70 and 60 and 63? That was on TV. 2012, 5 years ago. So it has to be 100%. Okay. Scientifically, these guys produce pie chart as you see. You like them? Why? There's too much colors in there. You cannot even read the labels. I have no idea. Amazing science, don't get me wrong, but they overlooked their chart. Right? How about here? There's a fundamental issue with that figure. Fundamental. And you have to tell me.
There's too many labels.
Yeah, the labeling is confusing. I agree. What else?
Colors as well.
There is no percentage. Thank you so much. These are frequency. 200 and 775. What? Percent? What is that? This is a histogram. You're producing a histogram as a pie chart. Because histogram is about counting the number of frequency of whatever you're looking at. These are frequencies. The frequency of biological whatever, it's 109, 75, 775. So this is fundamentally incorrect. Right? It has to be part of a whole. I don't know the total here. What they should have done is they calculate the total and divide each of these numbers by the total, then it becomes something meaningful. So there's a missing step. This is published in Nature, Scientific Reports, about 2 years ago. NASA, they are giving, that's in the website, you guys can go and look at it, the total fund for a project FY08. And each of these are the projects and how much they are getting from the whole pie of total fund. You really can't quantify the differences between these projects and how much they are getting? And this is NASA. How that happened? This pie chart was published in Science. I don't know, I cannot even read. 2010, and as you can see, you may have, you may say like the colors are not good. It's really bad choice of color. I agree. And I don't know why explaining. This is just a pie chart, and I see text beside a pie chart. That's weird. Are you explaining dynamics or a process, or why are you doing that? Is that for teaching? Is that pie chart for teaching, and therefore I have to put too much text to explain what the pie chart is about? Again, guys, look at the colors. You're not going to appreciate it so much. This is very nice. Scientific reports, and you can. What do you like about that pie chart? It's 2D. Thank you. Thank you. That's a very good beginning. It's 2D and it has the percentages and it's ranked descendingly, so I can follow, right? Because
some percentages are missing.
Yes, I agree. There are some percentages. The last 3 sections are missing the percentage. I agree. So that's what they should have done. Thank you for the suggestion. Good. You guys are very critical now. You're gonna produce amazing figures. I presume from now on, your figure production is gonna be completely different. Line chart. What do you think about this line chart? Rule of thumb. If there is an overlap between the lines, I think you are using the wrong chart. Why? Because it's very difficult for anyone to see the differences. If they are overlapped, how are you going to differentiate? This is published in Nature Energy. It's very, well, let's wait a second. Data visualization is to amplify cognition. To have a complex scenario, make it simpler for me to understand. Now that's more complicated now for me to follow. And the coloring. And red for colorblind people. Okay. What do you suggest for these guys? The scale. That wasn't a good choice. How about you just take this legend, move them to the back or the end, far right, and then zoom in so I can see the amplitude even more, right? Nature. Huh? What is wrong with that? Do you really can differentiate between these guys? That's absolutely 100%. That's almost 100% overlap. Like even the previous chart was like kind of there's some overlap. So this is like almost identical. The left one, you appreciate the left. Yes, the left one. So my left is your left, I believe. So the left one here is, you see the lines. They are separable, but there is something funny. Colors. they use the same color. They use the red color 3 times. However, the symbol for each of these lines is different. One is triangle, one is diamond, and one is circle. So why do you do that? You use the same color. Let's go for the nature biotechnology, the one at the right side. Beautiful. They are separable, quite nice, and yes, they may need to take care of the red color in the future. But there is a line for, I don't know what that line is about. Why you leave that line there? You see that line? See? Yeah, that one. What is that about?
Your conference is scheduled to end in 2 minutes.
Wow. Scatter. Can we have more?
Just for recording, but we're not supposed to touch it.
So, should we end now?
The recording will end in 2 minutes.
Okay, so we're gonna continue, and so here's a scatter, and if you want to scatter data, that's how it looks like. You have lots of data, you see like sort of correlation, you scatter them, and then you do some linear regression. That's a line, you see a trend. You need to report the sample size when you do that, because this is too many points up there. It's hard for anyone to understand. The linear, the line that you produce, you need to put the equation of that line. I'm going to show you an example here. Yeah, that's a very nice example. You see, we put lots of data scattered. They put the equation, they put the correlation coefficient, how correlated they are. We can discuss that in the statistics class. And then the number of subjects. And then you see the labeling was very easy for me to follow. The Eastern Rivers, neither, for each symbol. That was very nice. Bubble chart. I have no idea what that figure about, but I don't think anyone will know. Overlapping you cannot understand anything. This is a very interesting chart published last year in Science. It's about how innovative employees are and the respect they're getting to be loyal. Okay, so there's 3 parameters here.
Your conference is now over. Goodbye.
Goodbye. So you have